Next slide. Well, we also see many beautiful things like the northern lights or the southern lights, the auroras that are associated with our planet. Now, what these are for the students are when the sun has what's called a cosmic mass ejection. The sun throws off a bunch of particles,
solar flare,
and if they happen to come toward the Earth, then when those particles hit the magnetic field of the Earth, they travel along the magnetic field toward the poles, depending upon the charge. It'll go to the North Pole or the South Pole, and when they hit the atmosphere, there's photons emitted, and it creates the currents of light that we know as the northern lights in the northern hemisphere, aurora borealis, or the southern hemisphere, the southern lights, or aurora australis. Okay, and what's really neat about this is the magnetic field of the Earth acts like a force field to protect us here on the planet. Indeed, on Mars, which was very similar at one point in its history to the Earth, in that it also had a magnetic field. It had an iron core, liquid iron core, that created the magnetic field around Mars. But its iron core has long since cooled and solidified, so Mars no longer has a magnetic field. And as a result of it not having a magnetic field, the solar wind has been stripping the atmosphere of Mars and been making it thinner and thinner over the last several million years, and to bring it to the point where we have today. Because in the past, at one point on Mars, we know there was liquid water and rivers running on its surface just like they ran on Earth. And that tells us that if there were possibly water on Mars, which there still is in the form of ice and vapor, that there might have been a development independently from Earth of life on Mars. Okay, so we've just seen some examples of what we can observe from space. They were beautiful, they were great pictures. We can use the assets in space to do much better work. Here's a picture of a glacier that was taken in 2001, and this is a more recent picture, and this yellow line is where it was in 2001. This is more where it is today. So we actually got a picture from space of the glacier's position actually receding somewhat. And here's a picture over the Gulf of the United States. This is taken from a weather satellite at 22,300 miles above the Earth. You can see here across Florida a cold front.
Florida,
this is Florida. Here's the Cape Canaveral launch center for the U.S. launches the space shuttle and other rockets. And here's a cold front. What I'd like you to look at in this picture is this area of the cold front right here, especially where this line is here, the break of clouds. And notice the V shape. This happened to be a photograph of that same front taken from the space shuttle. We can see the cold front, the shape, the V shape. This is south in this direction. Here's that little break in the clouds. But we can see that the cold front, that as cold air moves in this direction toward the upper right of the picture, and there's warm air in front of it, the cold air acts like a snow cloud to push the warm air ahead of it, and then it rises up above and produces all of that violent weather. The International Space Station covers about 75% of the lands of the Earth's landmass, where 95% of the world's population lives. So we can use the space station as a remote sensing platform. But how are we going to do that? One way we do that is by installing on the space station optical quality windows that face the Earth. You're looking at the bottom of the space station as if you were looking straight up at the space station passing overhead. That's what the bottom would look like if you could see it close enough. Well, on the bottom, there's this window here. Here's a blow-up of it. This is in the U.S. Destiny Module Laboratory. Here's another even larger blow-up of it. It has a shutter on it to protect it when we need to protect. Here's a view. I thought I'd just throw this in here so you have a view of what it looks like to look out the window from space. Anyway, there's a picture with the shutter closed. Now, this window is made along the lines of the way the Hubble Space Telescope mirror is. The surfaces on each surface of the glass is very, very highly polished to give us extremely high optical quality. And what that does for us, it allows the light to come from the outside of the space station, inside the space station, to cameras and sensors we might put inside, such that the window doesn't bend the light or distort it or cause blurring. Now, as good as those pictures are that I just showed you, to us in the remote sensing business, they're terrible. They're actually very blurry, and we can show even better pictures we can share that spaceflight experience with even more vivid, more colorful pictures down here on Earth for all of you if we install optical quality windows on our spacecraft in the future. But for this one, we can even take it another step. This is an example of what the window looks like. It's actually 4 panes of glass. This one is removable, and so we're left with, there's these two joined together, and this one. Here's a cutaway side view. So the glass we look through is actually several centimeters thick, and the total of all 3 panes is about 6 inches. Several, maybe about 8 to 10 centimeters. This window, like I said, was highly polished and very, very carefully calibrated to allow us to use it for remote sensing. This is the transmittance curve of the window. In other words, what kinds of light can pass through it. You can see here, this is the visible spectrum. Here's the UV. Now, UV is harmful to people. We get sunburn, it hurts our eyes, produces cataracts. So we made the window so it doesn't pass UV. There's no transmission in the UV, so it's safe for people to operate. It also transmits almost 100% of the light through the window without being adulterated. So it's almost as if the window isn't there. That's how good this window is. And then it also transmits in the infrared section of the light, and that's what allows us to be able to do multispectral and hyperspectral remote sensing. Just to give you an example of the differences in the types of pictures you get from a normal window, this particular photograph would be through this chart taken through a space shuttle window with a very large camera lens. This is the difference of the same photograph you would get taken through the science window that we have for the space station. Next slide. This is an example of the ground resolution you would get. Go to the next slide. So we can actually see things and image them down to 1.5 meters on the surface of the Earth from the space station through this window. But the window by itself is useless without some way to take your instrument and mount it and power it and command it and then collect the data from it. What we did to do that is we created what is called the Window Observational Research Facility, a Klingon character in Star Trek The Next Generation. Yes, it is named after him. Inside the wharf, she was our technician to install it. The wharf just went up this year. It's been waiting to launch for 10 years. That's how long we've been trying to get it on board. It was scheduled and then rescheduled and then rescheduled. We finally got it up there and we're going to be able to use it now. This picture, you can see, is inside the payload volume of the wharf, where the cameras and instruments and sensors will be put to look out the window. This is where the astronaut would be in the aisle. There's the window in the hull, and that's a cutaway section of the wharf. It houses sensors and payloads for various purposes. We have EarthCam up there, which is a very educational picture taking where students take pictures of the Earth from schools, and they actually get the pictures down in their classrooms through the window. We have what's called ISAC, which is a very, very new payload on board. It's called ISS Agricultural Camera, and it is used to monitor agricultural interests in the northern part of the United States. And that will be operational early next year. And matter of fact, it's operated similarly to Victor's Aerocosmos system, where we would take images, customers would request images, the images would be taken, they would be brought back down and delivered to the customer. It is to help monitor their crops in the field as they grow through the growing season. One advantage is that remote sensing satellites normally only pass over the same point on the ground once every 16 days. If the crop gets sick, and you take a picture of it now, it's only going to be 16 days with the satellite up above, but with the ISS, I get a picture the next day, and I can detect diseases and problems with the crops that I might not be able to detect otherwise. And I know it's been a long day, and it's nightfall in Kuala Lumpur. Thank you.